Sound and light. Dalek sound. Dalek light. Start a new unit on waves and sound. So in this unit, we're dealing with waves. Waves are transfer of energy like we did first semester, except this time it's a disturbance. Oh, sorry. It's not liking my pen right now. A disturbance, not an actual physical transfer. And so instead of a ball moving through space, I'm just hitting a bunch of balls together and they're hitting each other, and the disturbance is what's propagating through space. That's what a wave is, a disturbance traveling through space. And since we usually send more than just one, there's a certain number of disturbances per second. That's our frequency. It's the number of cycles, the number of disturbances, the number of times I hit something per second. 1/seconds is called a hertz. And along with frequency comes period. Period is the opposite of that. It's how much time it takes for one cycle. We've already talked about period a bunch, and this main equation, frequency equals 1/period, is because one of them is cycles per time, the other one is time per cycles, and so they are the opposite of each other. When dealing with waves, we have to do some vocab. We have to deal with waves, and this right here is one type of wave. This is a transverse wave. Transverse. Talk about the two different types. But this is like I have a rope here, and I'm disturbing it up and down. I make it go up and down and up and down. It makes a little, looks like a sine wave. And I have to talk about some things. Equilibrium position is where my rope would be with nothing on it. So that would be my equilibrium position. The highest point in my wave is called the crest. The lowest point is called the trough. The amplitude is how much I disturb it from its unstretched length, either up or down. I don't usually put negative in there, I say how much it is. And then the wavelength is from crest to crest or trough to trough. In fact, from the beginning to the next beginning. Any position that's the same in each wave. And the Greek letter for wavelength is lambda. And so it looks like this, or like an upside down Y. And if you think to yourself, it's a lamb, duh, you can draw it in as a little lamb here. I'm going to do my best to make a lamb out of this. That's 2 feet. I'm going to put the other 2 feet on, and a little fluffy tail. That's the worst lamb I've ever seen in my life. I'll try to make a better one on the board. But lambda, it's not a lamb. It's a lambda. Get it? Lambda. Just like for particles, we had a main equation, F equals ma, or you can think of velocity equals distance over time. We have a main equation for waves. The main equation for waves is that the velocity of the wave is equal to the frequency times the wavelength. Notice that's the same thing. Velocity is distance over time. Lambda is a distance. Frequency is a 1/time, so it ends up being distance over time. But it's using different kinds of words, and we use this just as much as we use F equals ma or other things, just with waves, light, sound, ocean waves, lots of different kinds of waves. Wave phenomena are almost as prevalent as actually moving things, so we do it a lot. We have two different types of wave. A transverse wave is when we have like a slinky and we push it up or down, and it makes like a sine wave. That's the disturbance is at 90 degrees to the way it's moving. So it's moving this way and I'm disturbing it up and down. But there's also what's called a compression wave. Longitudinal is another word for compression wave. And essentially I'm taking my slinky and I'm pushing it closer together. And so the direction of travel is the same as the direction that I'm disturbing it. And things get closer together and farther apart. We'll have a slinky in class, I'll show you that. You need to know the difference between those. A great example of a transverse wave is light. And a longitudinal wave, sound is a longitudinal wave, because when I make sound, I'm pushing the sound molecule, the air molecules closer together and farther apart, like with a tuning fork. They're closer together, then they're farther apart, closer together, farther apart. Those compression waves getting closer and farther apart hit your eardrums. That hits the anvil and the stirrup and goes into the word cochlea thing, and that's how you can hear sound. Ocean waves are a combination of the two. See if you can figure that out or look it up. The principle of superposition tells us what to do if two waves are going to occupy the same space. Because if it's a disturbance, I can have a disturbance going one way and the other way. The blue one's going to the left, the red one's going to the right. So what happens when they would occupy the same space? And so these dotted lines on this line right here are where the waves would be on their own. And to find the combination of them, what we do is we add their amplitudes. And so if I drew a straight up and down line and saw these amplitudes, my blue wave, the one on the bottom, would give me like a -1. It's down 1. My red wave is going up. That would give me a +3 there. And so when I add them together, I get a +2. And so my wave ends up being right about there instead of up where the dotted line is. There's always going to be a spot right in the middle where the amplitude of my one wave and the other wave are positive, negative, the same thing, and then I get nothing. I'm going to keep adding my amplitudes. We're going to do this in class a little more detail. But essentially, you see how far away each one of the waves is from your unstretched length, and add those amplitudes at each point to figure out where the wave is going to be. And there's some examples. The nice thing about waves is that once they get past each other, they retain whatever shape they had originally. So this blue wave was over here, but now it's over here, and it's the same shape. The red one goes through it. It's on the other side. They pass right through each other. The weird part about that is that there is one moment where the red one's like that, the blue one's like that, and when I add their amplitudes, I get exactly 0. And so my rope is going to look straight, even though there's two waves about to go through each other. In a couple seconds, there'll be two waves. Right then, you see nothing. That is called destructive interference. The other weird thing about waves is they bounce differently, depending upon whether the medium is free to move or not free to move. What's called a fixed end reflection is if I have a rope and it's tied to a wall. If I have a rope that's tied to a wall, my pulse is upwards going in. When it hits the wall, it flips over and it's going to be upside down after it bounces off of that. And that's true of any kind of wave. If I have a free end, in other words, if I have a ring that's around some kind of hoop over here, so this is free to move up and down, not fixed, if it goes in on the top, it comes back out on the top as well. And so if you constrain it, it flips over. If you don't constrain it so it's free to move, it comes back on the same side that it started on. And so the kind of bounce that you have changes the wave. And that has big consequences later on when we talk about how these waves add together. And let's do that. Waves can add together in lots of different ways, but one of the most common ways is called a standing wave. We get a standing wave when we have two identical waves moving in opposite directions. So if I have a red one and a blue one, one's going to the right, one's going to the left. If they occupy the same space, like this one right here, the blue and the red one are in the same space, I'm going to add them together. I'm going to get a really big, maybe I should pick a different color, wave that's the addition of those two. But as they keep moving, in a couple seconds, they're going to cancel each other out and get nothing. See, right on this one right here, after they've moved, I get nothing. Then in a couple seconds, they're going to add again, but the other way, and so it'll be down this way. So what ends up happening with a standing wave is your wave goes up, nothing, down, nothing, up, nothing, down, nothing, but in opposite directions, one and the other one. And when I get this linky, it's easier for you to see in class. But standing waves means that every little bit that I add going in one way or the other way is going to add together to give me a really big amplitude wave. And so every sound that we hear is due to a standing wave of some sort. So every instrument, be it a guitar that you pluck or a trumpet that you blow, is because you get a standing wave in whatever string or column of air that you have. That's the only reason that you can hear it, because otherwise the vibrations would be too small. When you do a standing wave, there are certain points that move a lot, like this part right here, which is called an antinode. Then there's parts that don't move at all, like are always on the unstretched string. Those are called nodes, the ones that don't move, and antinodes are where they move a lot. You can write those definitions down for now, but we'll show you in class on a slinky, and it'll be really obvious where the nodes and antinodes are. And the distance between nodes, since the whole thing, if you look at the blue one, the whole wavelength is like from there to there. The distance between nodes is half of that wavelength. So a lot of times they'll ask how far it is from the 5th to the 7th node, and the distance between nodes is half wavelength. Find the wavelength, and then multiply by how many nodes you have, and then you can figure out how long it is from the 2nd to 7th node, or anything else like that. Just know generally how standing waves works, and I realize you're probably not going to get it quite yet, but it'll be obvious. So we draw standing waves as if they had little lobes on them, and really this is moving back and fourth there, and these parts aren't moving at all on a standing wave. And those are this part's the antinode, and these two parts are the nodes. And we know the distance between nodes is half of a wavelength. And so the first standing wave that you get on a string like this, to get them to add up with each other, I need to have a node on both sides. So when they flip over, they're going to add with each other each time. And so I get a node on both sides. And so the first fundamental frequency, the first time I get a standing wave on a string, is going to be half of the wavelength, because distance between nodes is half the wavelength. But I get another one. If I change my frequency until I get double the frequency that I had in the first one, it turns out that one whole wavelength will go between the two of them, because I get a node on both sides this time. And so then the length of the string will be exactly the length of a wavelength. Then I get another one where I have the second overtone, or the third harmonic, first harmonic, second harmonic, third harmonic, where I get 3 little loops, and that's 1.5 wavelengths. And notice that I could do a fourth one or a fifth one or a sixth one, just adding a loop each time. Essentially, it's n times whatever my fundamental frequency was, and my wavelength gets smaller each time by a factor of wavelength divided by 2. So every string has a certain frequency, or a set of frequencies, the fundamental, the first, the second harmonics, that a standing wave would form on that string. And so when you pluck a string, you're actually making all sorts of different frequencies. What you hear is the one that happens to make a standing wave on it, because every little bit adds up and adds up and adds up and makes a sound that you can actually hear. And that's because the string has a natural frequency. We put all frequencies in it, but the only one that you actually hear is the one that is the natural frequency. So that when you put your finger down on a violin, for instance, you're changing the length of the string, you're changing the natural frequency that plays on that string. So when you put your bow across it and make every vibration there is, a different one hits its resonance, and so you get a different note that you get to hear. Because of that, you get to hear notes. But if you get a standing wave on something else, like if you get it on a wine glass, you can destroy it. That can happen in buildings. And so the real danger in an earthquake is not the actual shaking of the earth. It's that shaking of the earth happens to be the frequency that's the natural frequency for skyscrapers. And if we get a resonance building up in a skyscraper, it can lead to the whole thing shattering and falling down. They actually had some problems with this on bridges, like because armies used to march in step at a certain frequency, and that frequency happened to be the frequency that was a natural frequency for bridges. They could actually tear down a bridge, and they had to train soldiers to stop marching in step when they got to bridges. Weird, I know, kind of crazy. It's due to natural frequency. And there was actually something where the army was trying to find the natural frequency of people and have these weird sound weapons that would shatter people apart. They actually could do it. The problem was it had to be really tuned well, and it was hard to distinguish between your body on your side and the other side, and all sorts of bad army experiments. Bad. So we talked about standing waves on a string. A standing waves on a string has to have a node on both sides, and so you get loops that look sort of like that with a node on both sides. It turns out that in an air column, like a trumpet or a clarinet or anything that has air in it, if you want to get a standing wave on an open end of an air, it needs to be an antinode, not a node. And that's because, remember, if you have a free end, and an open-ended pipe is like a free end, you want it to flip back on the same side, and so you want it to be back on top of itself, and so as it goes to the end, you want it to come back on the same side, and so you want an antinode to be there. If you have a fixed end of a pipe, one end closed, you want to have a node there. And so if a general form of a standing wave looks sort of like this, the smallest bit that'll have an antinode and a node is a fourth of a wavelength. And so that's this right here. I have a node on that side, an antinode on that side. That's a one-end closed pipe organ. I can get that again with a higher frequency or a longer tube if I have the same frequency when I get a whole loop and then a half a loop, so 3/4 of a wavelength. Or if I get another loop, I could get 5 wavelengths over 4. Notice in an air thing, it's actually a compression wave. So it's actually moving a lot at an antinode and not moving it all at a node. but that's hard to draw and hard for us to visualize. So I drew them as transverse waves on these up here, even though this is really what's happening. And if it's one end open, one end closed, I need to have a node on one side, antinode on the other side. So I start with a wavelength over 4, and every time I go up one, I add wavelength over 2, because I'm adding another node in there. If I want both ends open, I have to have a antinode on both sides, and so the smallest bit I can get is like from there to there. And if this is a full wavelength, from here to here, if I take the middle section, middle 2/4 is a half, I get wavelength over 2. Then I can put another loop, I get wavelength, put another loop, it's 3 wavelengths over 2. Our AP test only does the first 3 harmonics, and if I remember what I start with, half of a wavelength when it's both ends open, wavelength over 4 if one end's open, one end's closed, and I remember that I go up by half a wavelength each time. I can figure out a bunch of stuff about that. And a lot of times they'll say, okay, I know what the wavelength is, how long of a tube will I need for the second harmonic? So you know the second harmonic is wavelength over 2 plus wavelength over 2, so it's a full wavelength. Find wavelength, usually with velocity equals frequency times wavelength. Find that wavelength, and that's the length of my second harmonic. If it's the third harmonic, it's 3 of that divided by 2. We'll have some problems with it. It's not difficult, and I know it looks a little weird. We'll talk about it in class, but not too bad. Okay, we have a new snack theme for this unit. It's not one that I'm proud of. This unit snacks are snacks that I hide from my family. I love Cadbury Fruit and Nut Bars. I love them so much that I don't want my family to eat them. They're like other chocolate. It's not their thing so much. When I get one of these, I put it on the top shelf, way in the back. I also like to savor it. My family eats things right away. So I'll put it in the back. I'll let it sit there. Sometimes I buy some other chocolate and put it in the front so they know about that and I can't get to my good stuff in the back. This really is my favorite chocolate. I don't know why. I don't really like raisins, but you put raisins and almonds in chocolate. Wow. I really like it. We're going to get this. I'm going to eat this for the rest. And for 8.2 and 8.3, we'll talk about other things I hide from my family. Guilty pleasures. Okay. Doppler effect is what happens when the thing making the sound is moving or the person listening is moving. Let's talk first about the thing moving. If we have something not moving, it's just sitting there, it's going to make a wave, and then in a couple seconds it makes another wave, which is this one, and then the first one's gotten bigger and bigger. And so if I'm standing over on this side or on this side, I'll hear a certain number of waves come to me per second. That's the frequency, that's the tone I hear of sound. But if I go down to here and I say this is my first second, third second, fourth second, if my object moves, if I put it on a skateboard for instance, I'm going to make a wave here at this first place. Then it's going to move forward. I make a new first wave, but the wave I made before is centered here. And so it looks like that. As my object continues moving, I'm going to have something there. The next wave is centered here. The very first wave is centered there. What ends up happening is my waves bunch together on this side and get farther apart on this side. And so if my source is moving towards me, if I have a skateboard with wheels and I'm going that way and I'm standing here, I will hear a higher pitched noise. So I want my frequency to go up. And so this velocity of a source has a plus and a minus for when it's going towards or away. To look at my situation and see if it should go up or down. So if it's coming towards me like this, my frequency should go up, so I want to put a minus in the denominator here to make it go up, because when I make the denominator smaller, my frequency goes up. If I was on this side of it over here, I'd want it to go down, so I'd put a positive on it, and then it would go up. Now I can also take my observer, my person, and say I'm going to run away from it. If I run away from it, that should make my frequency smaller, because fewer of these waves hit me. So I need to look up here on the top. To make it smaller, I'd want to put a minus up there. If instead I ran towards it, I should make the frequency greater, and I would want to make a plus up on the top to make it greater. Notice if I'm moving both the source and the observer, they cancel out and I get nothing on that frequency. So the positive and negatives, you kind of figure out from your situation. Like this tells you about the source, but it's easier just to think about the situation and make sure you get it right. This is the race car noise. So when you're at a racetrack and a car is coming towards you, the frequency should be high, so you hear a really high-pitched noise. It goes, eh. When it's past you, it should be a low-pitched noise because it's past you and you're going to have the lower-pitched noise because you go, oh. So what happens is, as the race car goes by, it goes, meow. Same thing with a train. And since I'm sure you want me to do it again, I'll do it one more time. The race car goes, meow, as it goes by you. If you look at this picture over here, we have a plane not moving. When it starts to move, they bunch up on one side and not on the other side. But as I get close to the speed of sound, notice all my waves are piling up on top of each other right there. That was what they called the sonic barrier. Because when things got close to that speed, little small vibrations would pile up, and end up ripping apart a bunch of planes. And so they thought there was a wall there. You would get to the speed of sound, and as you hit it with your plane flew apart. And lots of people actually died doing that. And so they thought they would never be able to go faster than the speed of sound. But it turns out that once you get past that, that's the supersonic business, the waves no longer pile up. They start, you start making waves in front of the ones that were being made before. And you get to it. So as you get closer and closer to the speed of sound, it gets louder. But when you go through the sound barrier, sound all goes away and it's nice and smooth. There was one problem though, because as these waves are building up, you still get a little pressure wave. It looks like that. And so the shape of a regular plane at the time they were breaking the sound barrier was like this. And what happened was you get the pressure barrier like that, and so it ripped off the plane wings. So what they ended up having to do is they ended up having to change the shape of planes so they fit into that little cone made by the sound. And so all supersonic jets have to be little wedge shapes so they don't get their wings ripped off. Kind of cool. Last little random formula is a beat frequency. It's when I get two frequencies that are close together. Close frequencies. And what ends up happening is at certain points when you do principal superposition, like right here, notice they're both up and so they'd add. But as you keep going on, now one is up and one's down, and so they would destructively add instead of constructively. So you end up getting a really high frequency and then it goes a low amplitude, and then it goes up high amplitude and then it goes low amplitude, and high amplitude and low. And the frequency of that going up or down, so if we go and say, okay, the frequency of that line right there is what the beat frequency is. So it's not a frequency as in a tone, it's a frequency of the noise going up and down. So it goes wah, 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 wah. It's actually how you tune any kind of instrument. You listen for that wah, 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 and you want to make the beat frequency get smaller until there's no beat frequency, and then you are in tune. That's how they tune pianos. He has a tuning fork and he plucks the string and then he listens. I mean, he has to listen a lot because he has a lot of strings in there. And he gets rid of the beat frequency by tightening or loosening it. If you've ever tuned instruments professionally, that's kind of what you do. We'll talk about it a little more in class. But notice this is an absolute value, so you have some odd math on that. So sometimes you know one of the frequencies and you know the beat frequency, and you know it could be above or below it. So you get two different answers. So like your beat frequency was 2 hertz, and you know one of your frequencies is 20. Your other frequency can either be 22 or 18 because there's an absolute value in there when you do that, and so you get 2 answers. All right, we are done with our Dalek sound light unit. I've got to talk about to eat. You got no homework tonight. All I gotta do, put 2 questions in that discussion. Let's try all of us to get one. Get done this time. I'll answer all your questions. I'm sure you got a lot.